Hello everyone, my name is Janet Kelsey of Separation Science, and I'd like to welcome you all to our latest webinar in collaboration with Mettler Toledo and the life science business of Merck KGaA, Darmstadt, Germany. Our topic today is how to fulfill regulatory compliance with your Karl Fischer titration process. Let me introduce our presenters for today's webinar. Bettina Strabjob is the Global Franchise Product Manager and Lead Expert for Titration at Merck Life Science KGaA based in Darmstadt, Germany. She has more than 20 years' experience in the instrumental analysis business, especially with Karl Fischer titration, general titration, reference materials, and diagnostics. Her responsibilities include improving and simplifying titration processes, driving new technologies, and advancing applications and reagents. She always works closely with the QC and application laboratories for titration, as well as with the R&D department to develop titration continuously. Bettina is a graduate engineer and holds a degree in chemical technology from the University of Applied Sciences in Darmstadt, Germany, and a degree as a medical technical laboratory assistant from the Medical Technical Academy, Esslingen, Germany. Thomas Hitz studied biochemistry at the University of Zurich and completed his PhD in 2003 at the Swiss Federal Institute of Technology, Zurich, in the Department of Material Sciences, and postdoctorate in 2006. He provides market support at Mettler Toledo and has more than 15 years' experience in application development, sales, and customer training, and as a technical advisor for product development. He provides support for complex automation solutions and is an expert in automated Karl Fischer titration. Before we begin, I'd also like to mention that the life science business of Merck KGaA, Darmstadt, Germany, operates as Millipore Sigma in the US and Canada. And so, without further ado, I'll turn the presentation firstly over to Bettina.
Thank you to Separation Science for the introduction. My name is Bettina and I welcome you together with Thomas to today's webinar, How to Fulfill Regulatory Compliance with your Karl Fischer titration process. And now I hand over to Thomas.
Hello and welcome also from my side.
Note, in the following presentation is an abridged and summarized interpretation of the text in the pharmacopoeia to explain how to perform a Karl Fischer titration application according to the pharmacopoeia. Always check the current original text of the pharmacopoeia to perform your own application. And here the agenda for today. First of all, we will give you an overview about the whole Karl Fischer titration process. Then we would introduce you in the quality assurance and the variety of regulations. Then we will have a closer look at the example of the pharmacopoeia as one of the regulations. And at the end, we will also talk about the OMCL guideline, especially if you use the Karl Fischer open method. First of all, let's talk about the Karl Fischer titration process. The first step is the system setup. We have to choose the reagents for our application, and then we have to add data from the certificate of analysis in the titrator software, for example, the concentration of the titrant or the shelf life and lot number. And then we have to prepare the system, which means to rinse the system to eliminate air bubbles from the burette and the tubes to avoid failures in our titration process. After that, we start with a pre-titration. This means we have to eliminate traces of water in the solvent and the titration cell to get a stable drift before we then can start with a titer determination or instrument check. The titer determination is necessary for the volumetric Karl-Fischer titration, and here we determine the exact concentration of our titrant. Additionally, we also correct deviations from the equipment and the environment. For the colorimetric titration, we just need an instrument check with an appropriate standard. Then we can start with our sample titration. First of all, we need to do a sample preparation, which means we have completely to release out the water from the sample, either by dissolution or extraction of the water. And then we can start the sample titration. At the end of a series of samples, we need to control the whole process. This we can do by adding a standard to the titration cell and check if we refine the value of the standard. Also, we can check with a standard the performance of our solvents after a series of titrations or the performance of our colorimetric Karl-Fischer reagent.
On this slide, we want to discuss what can be the reasons for incorrect or not expected results. First of all equipment needs to be maintained. This means for the titrator that the sensor inputs as well as the analog and mainboards need to be certified regularly. Also, the balance needs to be maintained, and one should use at least a 4 decimal balance for the Karl-Fischer titrators. Also, the burette, the correct burette volume has to be used. This means that the titrant consumption should be within 30 up to 80% of the nominal burette volume. The dosing unit should be maintained and serviced, as well as the double pin platinum sensor. One has also to make sure that the pins are, for example, not bent, and they have to be free of any debris. At the end, one can also perform a general system suitability test with a water standard in order to be sure that the equipment is working error-free.
Besides the equipment, all the reagents can influence the titration results. If we do not determine the exact concentration of our titrants with a regular titer determination, or if we use not the right solvents or solvent mixture, we also have to check the performance of the solvents and the colorimetric reagents after a few additions of samples. And for the instrument check, titer determination and performance check, we need to use standards, and here it's important that we have certified reference materials with an exactly defined value. Also, we can have influence from our environment, for example, temperature and humidity. High temperature deviations during the day can lead to different results because of the volume expansion of the titrant, and also high humidity in a laboratory can lead to drift problems and to entering more humidity in the titration cell. Therefore, it is recommended to work in air-conditioned laboratories to get a constant temperature and humidity. Although the user can influence the titration results by choosing not the right method or the right reagents, and also the handling should be considered that it's correct. Therefore, we need an exact defined titration process that every user know what exactly to do. Here I would like to explain you a little bit more detail the pre-titration, which is one of the steps in our titration process. Pre-titration means elimination of residual water in the titration cell. We have traces of water in the solvent, we have surface water of the titration vessel, and we have ambient humidity continuously entering in the titration cell. All this water need to be eliminated before we start with our sample titration or before we start with a titer determination or standard determination. And this means we have to add iodine to our titration cell, that the iodine can react with the water to eliminate this water. And after this elimination of water, then we can start with the sample titration. But before we start with the sample titration, we need to take care that we have a constant drift. Drift means the amount of water which is continuously entering in the titration cell, because the cell is never 100% tight. And this level of ambient humidity which is entering in the cell, we need to reduce from the sample result. After the pre-titration, it is important to do a titer determination, or also called standardization in some regulations, for the volumetric titration. Titer determination means correction of the titrant concentration, titration system, and lab conditions. The titrant concentration deteriorates gradually during storage and after opening. The concentration decreases on one hand by slow side reactions, for example for the one component reactions, because we have all reactive compounds in the titrant, and if humidity is entering in the bottle, then this slow side reaction can start. Also, atmospheric humidity contaminates 1 and 2 component reactions and decrease the concentration after a while. And therefore, we have to determine regularly the exact concentration of our titrants, but we also have to eliminate slightly difference of our instrument, electrode, titration medium and handling, and as well temperature corrections in our laboratory or humidity differentiations. What is the best standard for the titer determination? So we have different possibilities of standards we can use. They are sometimes also described in the regulations you have to follow. For example, in the pharmacopoeia, we have mentioned in the European pharmacopoeia the pure water and water standards as certified reference materials. The USP additionally also mentions the disodium tartrate dihydrate. What is the difference? We can use the pure or purified water, which is 100% water and therefore a high water content. Therefore, we can only add a very low sample size, which is 20 microliter, 2 drops. This relates then in a high weighing failure, and the sample is also difficult to handle. And therefore it often relates in a worse relative standard deviation, even if the personnel is not very well trained and educated. The disodium tartrate dihydrate has also a very high water content of 15.66%. It's a solid substance, and we have a bad solubility in methanol, which means we have to extend the steering time before we start the titration, and we also can have a saturation after we have added 3 portions, about 150 milligram in the solvent. That means then we have to change the solvent for an additional determination. And therefore the water standards in ampules as certified reference materials are quite convenient to use. They have a reasonable water content of 1%. It's a solvent mixture with an exact defined water content, which can be seen in the certificate. It's very easy to handle. We can add a reasonable weight and measure it easily with a low weighing failure, and therefore we have at the end a very good relative standard deviation. Therefore, we recommend to use water standard certified reference material instead of pure water or disodium tartrate dihydrate. For the colorimetric method, we just need an instrument check with an appropriate standard, because this is an absolute method. We have not to do a titer determination because there is no iodine concentration in the reagent. The iodine is generated in situ during the titration. There is no external addition, and we have just to do a frequent system check with suitable standards before and after a series of samples. So when we start with the first sample and probably at the end of the last sample, we can add an ampule standard 0.1% or 0.01%. And now we come to the jungle of regulations. What kind of regulation we have to follow depends on the segment we are producing products, the country we are producing the products, and if we export or import goods to other countries. And therefore we have to show what kind of regulations are relevant in our segment. We have ISO guidelines, we have AOAC regulations, which also contains a lot of food regulations. We have pharmacopoeias, we have ACS regulation, ASTM regulation. We have also to follow national laws and requirements, or we have an internal QA system, quality assurance system, which has regulation guidelines, GLP, FDA audits or audits from customer, and what is the specification we have to fulfill for them. So check before you develop your application procedure what you have to fulfill in the regulations. Many of you have to follow, besides the regulations for a specific segment, although internal quality assurance guidelines. And this means you have to standardize your process to avoid and prevent failures in the processes, to optimize processes and methods, and complying with the regulations, for example, the pharmacopoeias or food guidelines, and also to ensure a constant product quality. Quality assurance means to define exactly your Karl Fischer application process. First of all, define the purpose, then define the performance criteria of your analytical method, develop and evaluate it, and at the end define operating parameters and review the process to optimize and improve the process. What needs to be defined for your Karl Fischer application to fulfill quality assurance criteria? You need exactly to define, for example, the sample size, the reagent types, the use standards, the solvent amount and type. If you use a mixture, describe how many percentage from which solvent you use, the temperature in the lab, the humidity in the lab. Also define acceptance ranges, for example, for the titrant concentration. In some guidelines, for example, in the pharmacopoeias as described, you can only use a titrant if it has still 80% of the value from the supplier mentioned in the certificate. Then also the relative standard deviation you accept for your titer determination and the range in which you accept your sample results. Also define the intervals for the titer determination, define the exact handling, the used equipment, for example, that you have to use a balance with 4 decimals, or the kind of titrator, the syringes, the weighing boats. Also define the stop criteria for the endpoint, the intervals of the molecular sieve, which you change it, or the burette size of your titrator. And here we will have a closer look in one of the regulations as an example how to follow a regulation. Here the pharmacopoeia, which is one of the strictest regulations we have. And here we have the European and the United States pharmacopoeia. The European has the chapter 2.512, which is the volumetric Karl-Fischer titration, and the chapter 2.532, which is the colorimetric Karl-Fischer titration, and the USP has the chapter 921, which includes the volumetric and the colorimetric Karl-Fischer titration. So first of all, let's describe the volumetric Karl-Fischer titration, also mentioned semi-micro method in the European and United States pharmacopoeia. And you can see both have a paragraph of the composition of the reagents, and you can also see that the USP is sometimes a little bit more detailed in the description. The EP says that the water reacts with a reagent which has to contain a suitable anhydrous medium, an alcohol, a base with a sufficient buffering capacity, sulfur dioxide, and iodine. The USP also describes the preparation of a reagent with pyridine and methanol, which is not any longer state of the art to use pyridine as a base, because other bases are more improved and also lead to better buffering capacity and to better results. Therefore, and pyridine is also quite toxic and smelling, and therefore they describe also the commercially available stabilized reagent without pyridine can be used, 1 or 2 component reagents, and the alcohol should be methanol or any other alcohol like diethylene glycol monoethyl ether. They also additionally describe, if you would like to determine trace amount of water below 1%, that you should use a titrant with a concentration not more than 2 mg per milliliter of water. The reagent described above has 5 mg per milliliter.
All right, let us now have a look what equipment is needed in order to comply with the EP and USP regulations. First, we'll have a look at the volumetric Fischer titrator. So for sure, there is the need to have a titrant which is connected to the titration vessel. Also, a double-pin platinum sensor is needed in order to detect the potential or current change. Then a desiccant needs to be connected to the titration vessel in order to keep the air in the titration vessel dry at all times. Then an inlet for the addition of liquid solids and also for nitrogen and air is needed. Then a magnetic stirrer will be applied to continuously stir the reagent in the titration vessel.
So after Thomas has described the apparatus for the Karl-Fischer titration, now the standardization and pre-titration is described. First of all, both pharmacopoeias add methanol or an appropriate solvent into the titration cell and then eliminate the residual water from the titration cell and the solvent, which means this is the pre-titration we described before in more details. After that, they describe the standardization, or also known as titer determination. The European pharmacopoeias use certified reference materials or water, steering to the necessary time and do the titer determination. The USP also mentions, besides purified water, sodium tartrate, or when you use a commercial standard, it needs a COA which shows a traceability to a national standard, for example, a NIST standard. In the European pharmacopoeia, we also have mentioned that an open titrant or a titrant can only be used if it has still 80% of the value from the supplier in the certificate, which means this value is determined after production. Because of the decreasing of the concentration, it's only allowed to use it if it has still 80%. If it's lower, then you have to replace the bottle with a fresh bottle. And it also mentioned the standardization should be done always after opening the bottle, first use, and then in regular intervals. The intervals need to be defined by every laboratory. The USP says that after preparing a freshly solution or after opening, then you should do a standardization within 1 hour before the use, or if it's in use, continuously daily.
Let us have a closer look on the European Pharmacopoeia 2.5.12 on water semi-micro determination, the method A. In general, first one has to eliminate the residual water, and as soon as the physical drift is below 25 micrograms per minute, at the endpoint, one can regard the system as dry. Then one will directly inject the sample and the water will be titrated until the necessary extraction time has elapsed. Usually this is defined by a relative drift stop of 50 micrograms per minute at the endpoint. So as soon as the drift falls below 15 plus the start drift, this means relative drift stop, at the endpoint, then the titration is regarded as to be complete and the result will be calculated. Let us have a look on this slide on USP 921 on volumetric Fischer titration. According to the general chapter, the endpoint needs to be detected for at least 30 seconds. The increase of the flow of the current needs to be detected for this time. How can this be defined on a titrator? So one can define a delay time of 30 seconds, which means that at the endpoint this increase of current needs to be detected for at least 30 seconds. Alright, after method A, let us now have a closer look at method B on the water semi-micro determination. In this case, one will first add an excess of reagent, of Karl Fischer titrant, and this excess will be back titrated with a suitable reagent, for example methanol, that contains an accurately known quantity of water. For which samples might this be useful? This might be useful for samples that show a slow reaction in general, or also for solvents that show a slow reaction, and then also for samples that have a slow dissolution. Here we want to have a look how this Karl Fischer back titration is explained in the USB chapter 9.21 in method 1b. You can see that the wording is a little bit different, but also in this case an excess of reagent, the titrant, shall be added, and the not consumed excess of this reagent, of this titrant, shall then be later titrated with a standardized water solution.
And when we come to the sample titration, before we develop a new application, we need to do a suitability test with this new substance, which means we have to do a verification of the accuracy with the chosen titrant for each combination of substances. Titrant and solvent need to be examined together with the substance. This means we have to add the sample substance in our titration vessel and titrate exactly the water content. After that, we have to add in the same titration vessel 5 times sequential known amount of water corresponding to about 50 to 100% of the amount found in the substance. The USP describes test preparation and results, and they say use an accurately weighted or measured amount of the specimen, the sample, under test estimation to contain 2 to 250 milligram, or check if anything is specified in the monography. They also described how to calculate the minimum amount of substances to weigh in, which is described in a formula. And then they also give information how to handle specific samples. For example, capsules, they say you have to use a portion of the mixed content of 4 capsules. And if you have tablets, ground 4 tablets to a fine powder and use a mixed portion of it. Also, they say the temperature and humidity should be known and not influence the result when you do the sample preparation or the titration. Also, if the sample is hygroscopic, then you have to proceed fast and avoid moisture uptake by the atmosphere. Probably you also can work under a glove box.
In the European Pharmacopoeia 2.5.12, there is also the linearity check explained. So what is the procedure? So first, one titrates the sample of interest and quantitates the initial water amount. Then a linear regression analysis is performed by adding cumulative water, at least 5 determinations. Then one plots the cumulated water added versus the sum of the initial amount plus the cumulative water after each addition. Then one can perform the linear regression and calculate the slope and the x and y errors. Then, last but not least, one will check the acceptance criteria, which are 0.975, smaller than the slope, smaller than 1.025. And for the relative x and y axis intercept errors, these errors should be smaller than 2.5%. So first we applied this linearity check for the volumetric standalone system. Approximately 1 gram of the 1% water standard were added directly into the titration cell. And then cumulated amount of water, approximately 10 milligram per cumulated water addition, were added. After that, after 5 determinations, the linear regression analysis was performed, and it was found that the slope and as well as the x-axis and y-axis intercept were well within the tolerances allowed. Such a linearity check can also be expanded to a volumeter connected to an oven system. Typically, we recommend to add approximately 0.2 gram of the 5.5% oven water standard to verify the volumeter connected to our oven sample changer. This roughly corresponds to 11.16 milligram total water. So we wanted to check whether this sample size is within the linear range of the oven system. So we started with roughly 3 milligram as initial sample size, and then again we added approximately 10 milligram per each cumulated water addition. Then we performed the linear regression analysis, and we found that again the slope as well as the y-intercept and x-intercept error were within the acceptance range. For the listener of today's webinar that is interested in the setup of an oven system, we will cover it in an upcoming slide.
And now we come to the colorimetric Karl-Fischer titration. It's called micro method in the European and United States pharmacopoeia. First of all, they describe the principle and the reagents, and in both pharmacopoeias it's nearly the same description and in a little bit different words. The principle is based upon the quantitative reaction of water with sulfur dioxide and iodine in an anhydrous medium in the presence of a base with sufficient buffering capacity. Then they also describe that the iodine is produced electrochemically in the reaction cell by oxidation of iodide, and the produced iodine reacts at the anode immediately with the water and the sulfur dioxide in the reaction cell. The USP also says that when all the water has been consumed, an excess of iodine occurs, which usually is detected electrochemical and stops the production of iodine. Colorimetric Karl-Fischer titration needs as well a pre-titration before starting with sample titration, and both pharmacopoeias describe the elimination of moisture in the reaction cell and in the electrolyte reagents before you start with any sample analysis. Also, it's described you don't need to change the Karl-Fischer solution after each determination, because you can individual determinations carry out in the same reagent solution. You have only to fulfill the following conditions. Each component of the test mixture is compatible with the other components. No other reactions take place. So that means no side reactions with the reagents or the other compounds, and the volume and the water capacity of the electrolyte reagent is still sufficient. You can test this by adding a standard after a series of samples you have added, and check if you refine the standard. Then you can go on with adding samples. If you don't refine it, then you have to investigate if the water capacity or the samples occur any side reactions, and then you have to change the solvent. Colorimetric titration is normally for small quantities of water from 10 microgram to 10 milligram. Recommended for a good relative standard deviation is to add or work in a range of 100 microgram to 10 milligram, which means you can increase your absolute water content in the titration vessel by increasing the amount of sample size. Although the method and sample handling is described in the pharmacopoeias for the colorimetric titration, That means, as we already discussed before, we have to add reagent and then perform a pre-titration to a stable endpoint or a stable drift. And then we can add our sample into the titration cell and also titrate to a stable endpoint. Accuracy and precision are depending on the sample's preparation and the extent to which atmospheric moisture is excluded from the system. That means we have to avoid contamination with ambient moisture introducing into the titration cell or in the titration system. Also important is to measure the amount of baseline drift to keep it low. In the USP, although they described that the transfer of samples into the titration vessel as solution should be done by injection through a septum, and gases can be introduced into the cell by means of a suitable gas inlet tube to avoid any kind of contamination. The colorimetric method also describes how to handle solid samples. The European Pharmacopoeia says the introduction of solid samples directly in the titration cell should be avoided. If this is necessary, it needs to be done through a sea-level port and taken care to avoid the introduction of moisture from the air, such as working in a glove box with dry inert air, or the use of the Karl Fischer oven method is described. The USP says similar words. The introduction of solids into the cell may be required precautious, such as working in a glove box in an atmospheric dry inert air. Or they also say solid samples may be dissolved in a dried methanol or other solvent outside of the titration cell. Or if the sample is insoluble, the water need to be extracted with a solvent, and an exact measured amount need to be transferred in the titration cell through the septum then. Or also here the oven method is described to use.
On this slide, we want to have a look what equipment is needed in order to comply with the EP and USB regulations for a coulometric Karl Fischer titrator. First of all, again, the double-pin platinum electrode is needed to measure the signal. For the sample addition, a stopper with a septum for the liquid sample addition, but also for the gaseous sample addition, for example, for the gas phase extraction using an oven, is attached to the coulometric Karl Fischer cell. A desiccant inserted into the generator electrode is needed in order to keep the air dry inside the coulometric Karl Fischer cell. Then, of course, the generator electrode with an anode and a cathode is mandatory. That enables the generation of the iodine from the iodide present in the reagent. Last but not least, the magnetic stirrer will again keep stirring the reagent during the pre-titrations and sample titrations. Here we want to see how the coulometric Karl Fischer titration is explained in the USB chapter 921, namely method 1C. First of all, the iodine shall be generated in situ from the iodide by using a generator electrode with or without diaphragm. The double-pin platinum electrode will be used again as a sensing electrode to measure the signal change. Then we have the anolyte, or in case when we are using a generator with diaphragm, we will also have a catholyte. The sample addition shall be of the liquid type. This is strongly preferred. The water detection is for small water amount, so the optimal total water amount is about 1 milligram that can be added. And again, the detection of the excess of iodine at the endpoint shall take place. This can be defined either with a delay time or a relative drift stop, as we have seen previously.
The European Pharmacopoeia additionally describes the verification of accuracy, which means you can add a defined quantity of water, which should be the same as the sample, or better is to use a certified reference material and perform the titration. As mentioned also in the volumetric titration, if you use pure water, you only can add very low amounts of water, which leads to a high weighing failure and a difficult handling. Therefore, if you use a certified reference material, you can weigh in a higher amount, which reduces your weighing failure, and also the handling is more precise. At least you should add such a standard at the beginning of a titration series and at the end. And the recovery rate is within the range of 97.5% to 102.5% for the addition of 1000 microgram of water, and within the range of 90% to 110% for the addition of 100 microgram of water. And Thomas will explain you how to do this in the next slides.
In the following slides, we want to discuss the European Pharmacopoeia 2.5.32 on water microdetermination, so namely on the coulometric Karl-Fischer titration. As you may know, this is a titration that generates electrochemically the iodine from the reagent that contains the iodide. So we have an anode and a cathode that is able then to generate, according to the Faraday law, an exact amount of iodine that can be used to quantitate trace amounts of water, usually between 1 ppm and up to 5%. In this standard, it is mentioned that one shall measure between successive sample titrations a water standard. And they specify a limit for 1000 microgram and for 100 microgram for one single measurement. As you can see here, for 1000 microgram, the recovery shall be between 97.5 up to 102.5%. And for 100 microgram, between 90 up to 110%. So there are no exact limits given for the range between 100 up to 1000 microgram. So it's certainly recommended, if you want to stick to these limits exactly, also to either use 1000 or 100 microgram. Also, this single analysis or the single standard measurement is not applicable when an oven is connected. So the limits do not apply for the oven measurements. We will come to that later when we discuss the OMCL guidelines, which also reference European Pharmacopoeia 2.5.32. Let us now discuss how the OMCL guideline does apply the European Pharmacopoeia 2.5.32. So what is the OMCL? It is a public institute that is located in Europe and is in charge of controlling the quality of medicines and medical devices. They report to the national competent authorities. I copied here from the OMCL guideline their acceptance criteria. As you can see, for the recovery, the same limits are applied. However, they recommend to measure at least 3 standards, so that also statistic acceptance criteria can be applied. And as you can see, the statistics, so the relative standard deviation, shall be smaller than 2% or equal than 2% for 1000 microgram of water, and for 100 microgram of water, the relative standard deviation shall be smaller or equal to 5%. The linearity test that could be similarly done as for the volumetric Fischer titration is optional.
In both pharmacopoeias and the colorimetric part, the oven method is mentioned. This is because most of the ovens are connected with colorimetric instruments due to the fact that, as we already mentioned before, it's not recommended to add solid samples with low water contents directly in the colorimetric titration cell. And therefore, the oven method is here the alternative. The European Pharmacopoeia prescribes that you have to add the prescribed quantity of sample into the oven and heat it, which means we weigh in exactly the amount of sample in one of these little oven vials, close it tightly, and then after the evaporation of the water from the sample into the titration cell, we start the titration. They also describe an alternative method that the evaporated moisture is immediately titrated while heating the sample in the oven, and this is to avoid loss of evaporated water which is already collected in the titration cell in the reagent solution during the prolonged heating. They also mention you have to read the value from the instrument's output and then calculate, if necessary, the percentage or quantity of water which is present in the substance, and when appropriate to the type of sample and the sample preparation. Although they tell you to perform a blank titration. Blank titration means you add an empty, tightly closed vial before the series of your sample and determine the exact water content in the vial. And this is your blank, which needs to be reduced from every sample. In the USP, the oven method is described a little bit different. There are other aspects mentioned, and they say when appropriate, the water may be released from the sample by heating in an external oven which is connected to the titration vessel, and the water is transferred, the evaporated water is transferred with the add of an inert and dried gas such as pure nitrogen, or you can also use dried air. And they also make aware that any drift due to the transport gas should be considered and corrected. And they also say that you have to take care of the selection of your heating conditions in the oven, because you have to avoid the formation of water which is coming from the dehydration due to the decomposition of your sample. And therefore it is important when you develop a new oven application that you start with a temperature ramp to find out the exact heating temperature for your sample where the water is completely released out and the sample do not decompose it. And therefore now I hand over to Thomas. He will explain the oven technology a little bit more detailed.
This slide shows a schematic presentation of the water gas phase extraction. First of all, we have a gas input. This can be an air pump or a switch valve connected to a nitrogen bottle. Then we have the gas drying units, where the carrier gas is dried to a minimal residual moisture, which in the ideal case would be between 1 and 2 microgram water per minute. Then there is the gas flow meter, where the gas flow of the carrier gas is regulated to 25 up to 200 milliliters per minute. Then the carrier gas goes into the oven, into the vial via an inner needle and extracts the water from the sample over a certain time and leaves then the vial via the outer needle into the titration cell. And in this titration cell, there is the Karl Fischer reaction taking place over defined time period, as we already pointed out, usually between 5 and 40 minutes. Here on this slide, we want to discuss how the OMCL guideline applies the European Pharmacopoeia 2.5.32 on the water microdetermination in case an oven system is connected to the coulometric Karl-Fischer titrator. As you can see, it is also recommended to measure at least 3 standards. For the recovery, a limit between 95 up to 105% is given, and for the relative standard deviation, it shall be smaller or equal than 1.5%. In addition, also criteria are given for the temperature accuracy, stability, as well as for the gas flow rate. Now, I would like to summarize the water microdetermination on the coulometric Karl-Fischer titration. First of all, according to the OMCL guideline and also according to general practice, it is always better to measure at least 3 samples than just 1 sample. 1 sample can always be an outlier, and when measuring at least 3 samples, one can also apply statistics as acceptance criteria. So we certainly can recommend to apply to the OMCL guideline and to measure at least 3 standards. Also, the recovery is not for each single measurement. It is the mean recovery that is used to check whether the acceptance criteria are fulfilled. And the acceptance criteria are different for the direct addition as compared to the oven. We will now slowly come to the end of today's webinar, and Bettina and Thomas want to thank you very much for your attention. And if there are questions coming up, please write your question into the chat, and Bettina and myself will be happy to answer them.
Well, thank you both for that excellent presentation. We now have time for your questions. So our first question is, you mentioned the term physical drift value. Can you explain what this term stands for?
The physical drift is drift solely related to surrounding moisture, so water which enters the titration cell from the environment. A chemical drift would be more like side reactions, like you have with aldehyde and ketones, which will also increase the drift due to the side reactions. So the physical drift is only related to water entering the cell from the environment.
Thank you, Thomas. Right, okay, so we're going to go to another question, which is, how can we eliminate side reaction interferences when analysing samples of ketones or amines? It affects the accuracy of results, repeatability, and reproducibility, even when using specific reagents for such cases. So is that a question for you, Bettina?
Yes, so we need a little bit more details probably about the type of sample, if it's a liquid or a solid sample. Normally for ketone aldehydes, you really need specific reagents, methanol-free reagents, because the methanol is interfering with the ketone or aldehyde samples and is producing additional water, which then leads to this sluggish endpoints or not precise results. So, but you say you already have used specific reagents. I think we can send you an email and get a little bit more details about your sample to see what we can improve here.
Thank you, Bettina. And
maybe I can add a little
yes,
thing, is that usually it's difficult to completely suppress. With special reagents, you can slow down side reactions, but they will still occur. And after a certain number of samples, they will affect the results as well.
Thank you, Thomas. I think this question is for you, Bettina. How do you interpret the European Pharmacopoeia 2.5.32 accuracy requirement for a coulometer with oven? It's expected to have a recovery between 98 to 102% for standard determinations at the beginning and at the end of a run. And normally a system suitability test for a coulometer with ovens are standard determinations at the beginning.
Yes, so the pharmacopoeia only describes here the direct input of the sample in the titration cell for this accuracy. The oven method is not exactly described now in the pharmacopoeia and the accuracy, but Thomas in the presentation showed the OMCL guideline and related to the OMCL guideline. So Thomas, maybe you can here give a little bit more details. What's written there?
Yes, of course. So there is a broader range for the accuracy between 95 to up to 105% because you have a higher measurement uncertainty due to the larger system which is connected. Of course, very often you will be within the range of 97.5 up to 102.5. But overall, the OMCL guideline allows a broader range for the accuracy. And since this is basically for us the only point that we can reference, because there's not yet given in 2.5.32 any accuracy requirements, we comply to this OMCL guideline, which has a broader range for the accuracy.
That's great. Thank you very much, Thomas. So another question we have is, which standard is good for the Karl Fischer oven method? Is that for you, Bettina?
Yes, we have a specific standard for the Karl Fischer oven method with this organic substance with 1%. So it's relatively low in water content. And this standard you can heat up to 300 degrees Celsius, which means you don't have to cool down your titration system if you have a sample who is higher in temperature to evaporate the water. There are also other oven standards available. They are organic substances like lactose or citrate, but both can only be heated to 180 and the other one to 220 roundabout. And then if your sample need to be a higher temperature to release the water out or to evaporate the water out, then you have this problem in cooling down the system or heating up the system for the sample. And with the oven standard, you don't get this problem at the end.
That's great. Thanks, Thomas. Have you got anything to add to that?
No, I think that's fine. Yes.
Great. Okay. Well, thank you both again. And if any other questions do come in, I'm sure that Bettina or Thomas will be happy to respond to them via email. Thank you also to our scientific partners in this webinar, Mettler Toledo, and the life science business of Merck KGaA, Darmstadt, Germany. And with that, I'd like to thank you all for logging in and listening. Thank you and goodbye.
Thank you. Goodbye.
Thank you. Goodbye.